We continue now with the section 3.3 notes, and we're ready for example 3, part B, another example of synthetic division. We're going to divide x to the fourth minus 81 by x minus 3. First of all, our divisor has to be of the form x minus a to perform synthetic division, and in this case it's pretty clear that a is 3, positive 3. So that number goes in the upper left hand corner. The coefficients of f go in the top row, and notice the leading coefficient is 1, but then we're missing several powers of x to the third, x to the second, and x to the first. So all of those have to be written in with coefficients of 0. So we would write 1, 0x cubed, 0x squared, 0x, and then the constant term, negative 81. All of those coefficients are necessary to make the synthetic division work properly. Then we put in our little L-shaped thing, and we're ready to go. We bring the 1 down, we multiply. 1 times 3 is 3. 0 plus 3 is 3. So we add along the columns. 3 times 3 is 9. 0 plus 9 is 9. 9 times 3 is 27. 0 plus 27 is 27. 27 times 3 is 81. Negative 81 plus 81 is 0. Okay, so to interpret our result, the 0 is the remainder, which is constant. Here we have a remainder of 0, which means that the divisor here is actually going to be a factor of f of x. And then our quotient comes from the four other numbers in the bottom row. Remember that the degree of the quotient is 1 less than the degree of what you divided into originally, the dividend it's called. So our quotient here would be 1x cubed plus 3x squared plus 9x plus 27. Again, the remainder is 0, and we can say now that f of x has been factored as x minus 3, the divisor, times the quotient, x cubed plus 3x squared plus 9x plus 27, plus 0, which we don't need to write on the end. Now, I want to connect this to something that you would be familiar with from algebra, and that would be that normally in factoring x to the fourth minus 81, we would look for a special pattern, in this case a difference of squares, to factor it as x squared minus 9 times x squared plus 9. And then we would notice x squared minus 9 itself is a difference of squares. It's x minus 3 times x plus 3, then times x squared plus 9. Now the x squared plus 9 is a sum of squares which does not factor over the real numbers. Now looking at our two results, remember f of x is the same as x to the fourth minus 81 here. We have two different factorizations of x to the fourth minus 81. However, it turns out that they are compatible, because in the second form, if you FOIL the second and third factors, multiplying them together, what do you get? X times x squared is x cubed. I'll do inside first. 3 times x squared is 3x squared. Outside is 9x. And last is 27, which is exactly what we had for our quotient when we did the synthetic division. So to factor it by the usual method of using a difference of squares is compatible to what we did with long division. We're going to see, however, that in many cases, division really is the only way to factor a polynomial, because we will not see that the polynomial fits a particular pattern or form, such as the difference of squares. We now turn to some important results that are a consequence of the division algorithm for polynomials. The first of those is what's called the remainder theorem. The remainder theorem says if a polynomial f of x is divided by a divisor of the form x minus a, such as what we would see in synthetic division, the remainder is r equals f of a. That is, the remainder is identical to what you would get if you substituted a into the function. Now, to verify this, by the division algorithm, if we divide f of x by x minus a, we know that there's a quotient and a remainder such that f of x can be written as x minus a times q of x plus r, where we know r would be a constant. Anytime we do synthetic division, the remainder is constant. What if you substitute a in for x and compute f of a? Well, if x is a, then you get a minus a times q of a plus r, but a minus a is 0, so 0 times q of a is going to be 0, and it doesn't matter what q of a is equal to. So we get 0 plus r equals r. In other words, f of a equals the remainder r. So the remainder, upon doing synthetic division by x minus a, is always f of a. Example 4 says use the remainder theorem to evaluate f of 2, where f of x equals x cubed plus 2x minus 5. Now, we could obviously just substitute 2 in for x and evaluate f of 2 very easily without using the remainder theorem. But just to demonstrate how the remainder theorem works, what we would basically say here is that f of 2 should be is the remainder upon dividing f of x by x minus 2, x minus a, where a is equal to 2. So if we set up a synthetic division using 2 in the upper left corner, that is, a is equal to 2, and then using the coefficients of f of x, which would be 1, 0, 2, and negative 5. Notice we're missing the x squared term, so I have to put a coefficient of 0 in after the the leading coefficient. Put in the L, bring the 1 down, multiply to get 2, add to get 2, multiply to get 4, add to get 6, multiply to get 12, add to get 7, and we know 7 is the remainder. The remainder theorem would say that when we divide by x minus 2, the remainder should be f of 2. So, in other words, this should be f of 2. f of 2 should equal 7. Let's verify that against substituting directly into the function. F of 2 would be 2 cubed plus 2 times 2 minus 5, or 8 plus 4 minus 5, or 12 minus 5, or 7. So indeed, by doing synthetic division, we can evaluate a function. And we then know that the remainder is identical to the function evaluated at the value that we used in the upper left-hand corner, in this case, this number here, 2. Example 5 asks, what is the remainder upon dividing f of x equals x to the 99th plus 2x to the 50th minus 1 by x plus 1? Well, who would want to do such a division, an actual division, to come up with a remainder with such a high degree polynomial? However, if we use the remainder theorem, we can determine the remainder by simply evaluating into the function. X plus 1 has the form x minus a, where a is negative 1. So by the remainder theorem, the remainder upon dividing f of x by x plus 1 should be f of negative 1. And it turns out that f of negative 1 is easy to evaluate. F of negative 1 would be negative 1 to the 99th plus 2 times negative 1 to the 50th minus 1. When we raise negative 1 to an odd power, we get negative 1. To an even power, we get positive 1. Then we subtract 1. So it's negative 1 plus 2 minus 1. We're going to end up getting 0. So what's the remainder? The remainder is f of negative 1, which is 0. In other words, it follows that x plus 1 must be one of the factors of this 99th degree polynomial. So the remainder theorem allows us to determine a remainder without necessarily doing any division at all. We now conclude this video with a introduction to the factor theorem. First of all, recall that a number a is called a zero of a function if a function f if f of a equals 0. So a number is a zero of a function if, when substituted into the function, it causes the function to equal 0. The factor theorem says the following: let f of x be a polynomial. If x minus a is a factor of f of x, then a must be a zero of f of x. Conversely, that is if we reverse the statement, if a is a zero of f of x, then x minus a is a factor. So if x minus a is a factor, a is a 0. If a is a 0, then x minus a is a factor. In our previous example, we saw that f of negative 1 equals 0 for that 99th degree polynomial function. So if f of negative 1 equals 0, that is, the remainder was 0, recall, then negative 1 is a 0 of f of x. So by the factor theorem, if we have a 0, then we can construct a factor. X minus a, that is, x minus negative 1 or x plus 1, is a factor of f of x. So the factor theorem says that zeros and factors of polynomials are essentially two sides of the same coin. A 0 is not identical to a factor. A factor is not identical to a 0. But they are very closely connected. If you want to find the zeros of a polynomial, try to factor the polynomial. On the other hand, if you want to factor a polynomial, then find its zeros. Find its zeros. So we'll see that in trying to find zeros of polynomials, we'll look for factors. In obtaining factors of a polynomial, we'll easily identify zeros. They're two sides of the same coin. So we'll explore this relationship further in the following examples, which will be begun on the next video.